Welcome to Session 12, Integrated Data Analysis and Conclusions. A strong data answer connects evidence, correct computation, and a precise interpretation in context. 10 examples combine proportions, rates, resistance center, misleading scales, association, expected frequency, model error, polls, and complete academic conclusions. Identify the group and denominator, compute with units, then state exactly what the result describes without claiming more than the evidence supports. Example 1. A survey of 240 commuters finds that 90 use public transit. State the proportion and a complete interpretation. The key quantities are organized before the arithmetic begins. Plan, divide count by total, convert forms, and name the surveyed group. Step 1. Compute 90 divided by 240 equals 0.375. Step 2. Convert to a percent, 37.5%. Step 3. The evidence comes from the 240 surveyed commuters. Step 4. A complete statement is, in the sample, 37.5% of commuters used public transit. Quick check. Multiplying 240 by 0.375 returns the count 90. This matters in real life because transport reports need both an accurate calculation and a clearly defined group. Example 2. A chart shows store visits rose from 1,200 to 1,500, while purchases rose from 240 to 270. Did the purchase rate rise? The comparison places both cases on the same scale. Plan, calculate purchases divided by visits for each period. Step 1. The original purchase rate is 240 divided by 1,200 equals 0.20 or 20%. Step 2. The new purchase rate is 270 divided by 1,500 equals 0.18 or 18%. Step 3. Purchase count rose by 30, but visits rose faster. Step 4. The purchase rate fell by 2 percentage points. Quick check. Counts and rates answer different questions. Both statements can be true simultaneously. This matters in real life because retailers distinguish traffic growth from conversion performance. Example 3. A class has scores 62, 68, 70, 72, and 98. Choose and compute a typical score. The comparison places both cases on the same scale. Plan. Inspect the high value, then choose a resistance center if needed. Step 1. The value 98 is separated from the other scores. Step 2. The ordered middle value is 70, so the median is 70. Step 3. The mean is 62 plus 68 plus 70 plus 72 plus 98. Divided by 5 equals 370, divided by 5 equals 74. Step 4. The median of 70 better represents the main cluster. Quick check. 4 scores are near 70, while the high score pulls the mean upward. This matters in real life because teachers choose resistant summaries when a small class contains an unusual score. Example 4. A graph of 96 and 99 begins at 95, and a headline says performance quadrupled. Evaluate the claim. The bars make category magnitudes visible on one common scale. Plan. Use actual values rather than visual bar heights. Step 1. The numerical increase is 99.96 equals 3 points. Step 2. The relative increase is 3 divided by 96, approximately 0.03125, or about 3.1%. Step 3. The bars appear 1 and 4 units above the truncated baseline. Step 4. The word quadrupled describes the distorted bar heights, not the actual performance values. Quick check. A true quadrupling of 96 would be 384, not 99. This matters in real life because critical graph reading protects readers from exaggerated marketing and news claims. Example 5. A study finds a positive association between tutoring hours and scores. Write one supported and one unsupported conclusion. The comparison places both cases on the same scale. Plan. Separate description of the observed pattern from a causal statement. Step 1. Supported. Students with more tutoring hours tended to have higher scores in the sample. Step 2. This statement describes the positive association. Step 3. Unsorted. Tutoring caused every score increase. Step 4. The graph alone does not control study habits, prior achievement, or assignment to tutoring. Quick check. Supported language matches the evidence type and avoids absolute words. This matters in real life because education programs need stronger designs before attributing improvement to one intervention. Example 6. A bag has 5 green and 3 yellow tokens. Find the probability of yellow and the expected number of yellow draws in 160 draws with replacement. The key quantities are organized before the arithmetic begins. Plan. Find the single draw probability, then multiply by the trial count. Step 1. There are 8 tokens total and 3 are yellow. Step 2. P yellow equals 3/8 equals 0.375. Step 3. Expected yellow draws equals 0.375 times 160 equals 60. Step 4. About 60 yellow results are expected over many repeated draws. Quick check. The expected count is not a guarantee, but 60 divided by 160 returns the theoretical rate 3/8. This matters in real life because expected frequency reasoning supports staffing, inventory, and quality planning. Example 7. 2 programs report pass counts 45 and 60. Program A tested 50 learners, Program B tested 80. Which performed better by rate? The comparison places both cases on the same scale. Plan. Compute each conditional pass percentage. Step 1. Program A's rate is 45 divided by 50 equals 0.90 or 90%. Step 2. Program B's rate is 60 divided by 80 equals 0.75 or 75%. Step 3. Compare the rates rather than counts. Step 4. Program A has the higher pass rate by 15 percentage points. Quick check. Program B has more passes only because it tested more learners. This matters in real life because training providers compare rates to account for cohort size differences. Example 8. A delivery model predicts 28 minutes, but the observed trip takes 35 minutes. Write an evidence-based evaluation. The comparison places both cases on the same scale. Plan. Compare actual with predicted and quantify the error. Step 1. The model prediction is 28 minutes. Step 2. The observed time is 35 minutes. Step 3. The difference is 35/28 equals 7 minutes. Step 4. The delivery took 7 minutes longer than predicted, so the model underestimated this trip. Quick check. Adding the 7-minute underprediction to 28 gives the observed 35. This matters in real life because dispatchers track prediction errors to improve customer arrival estimates. Example 9. A poll of 400 voters reports 52% support. About how many sampled voters supported the measure, and what can be concluded? The key quantities are organized before the arithmetic begins. Plan. Translate the percent to a count, then limit the conclusion to the sample unless sampling is known. Step 1. Convert 52% to 0.52. Step 2. Multiply 0.52 times 400 equals 208. Step 3. About 208 sampled voters supported the measure. Step 4. Without information about selection, conclude only that 52% of the sample supported it. Quick check. The sample count 208 divided by 400 returns 0.52. This matters in real life because responsible polling reports both the numerical result and how respondents were selected. Example 10. A final report says, the mean weight was 14. Rewrite it as a complete academic conclusion when the data are pharmacy weights measured in minutes. The key quantities are organized before the arithmetic begins. Plan. Add the statistic name, value, unit, group, and appropriate scope. Step 1. The statistic is the mean. Step 2. The value is 14 and the unit is minutes. Step 3. The context is customers in the measured pharmacy sample. Step 4. Rewrite. Customers in the pharmacy sample waited an average of 14 minutes. Quick check. The revised sentence tells a reader what 14 measures and to whom it applies. This matters in real life because clear conclusions turn calculator output into usable evidence for service decisions. Session 12 Recap. Data analysis is not complete until a correct number is interpreted for the correct group, unit, and evidence source. Compare rates when group sizes differ, prefer resistant summaries around outliers, audit graph baselines, and separate association from causation. Quick check. 90 of 240 commuters use transit. What sample percentage is that? 90 divided by 240 is 0.375, so 37.5% of the sample used transit.